am the knight. Apparently. Can I get any lighting here, please? Okay. Okay. Oh my god, bro. Whatever, dude. I wanted to talk about this. Because I was reasoning through a bunch of things this morning, just kind of thinking, because, you know, yesterday I read chapters 5 to 6 of Category 3 for Programmers, and it gave me a lot to think about. So this morning I woke up and I was like, I have a few ideas. So in this video, this recording, I kind of just want to go through those, because I think they're quite interesting. There's a lot, like a lot. Like most of my thinking is just rambling in this one channel in this Discord server. Yeah. Like the rambling was so bad that like the moderator said, "Dude, make a channel." So I did, because I can do that. Right. So the first thing I was thinking was to do with tags. So there's a few thoughts here. The first one, and they're not really like not even that related necessarily, but the first thought was tags. So, you know, tagged union. What is a tagged union? I can't with this lighting. Like I need to like. Okay, what? Okay, bro. Tags. Why is it called a tagged union? Because there is a union with tags, right? The tags help you differentiate which is which. However, when are tags not necessary? Well, suppose I have a type that is an int or a string, right? Assuming that, oh my god, assuming that the only way that I can assign to one of these fields is by using the normal constructor, so like an int 5 or like a string, you know, and like I can't do some funky thing like pass a string to an int constructor and like constructor and it magically makes an int. Assuming that that can't happen, then I don't need a tag to know if it's an int or a string, right? Like if I have a thing that can be an int or a string and there's no overlapping morphisms basically to that type, then I don't need to have a tag. The tag is just the fact that it's either an int or a string, right? So that's fine. You don't really need tags when it's ambiguous. So the classic example is the maybe type. It takes a type variable a, right? And because it takes a type variable a with no constraints, it means that a can be anything. So not only can a be an int, a string, whatever, it can also be nothing. I could pass nothing to a. So like I could pass a maybe a to a maybe a, which then is a maybe a, right? Which means that I could have a maybe nothing, which means that I could have a nothing. And that's why I need to have just on the left hand side, right? So it's either just a or nothing. That's where the tag is important, because if I didn't have the just tag, then I could pass nothing into here, which would then collapse to like nothing or nothing, which is just effectively just nothing. And why is that a problem? Because, well, there are some instances where I actually do need to know if it's like nothing or just nothing. Like when I'm looking at like a map, for instance. That's an example that comes up. Apparently it's an issue for languages like TypeScript, where they do actually have the T, right, the T or nothing, have the T be untagged, or like T or nil, whatever. Apparently that does actually cause bugs. So that's not good. So what I was thinking then is, for these cases where you obviously do, like, where obviously having a tag for the edge case is important, then, you know, use a tag. But then have tag inference, because like most of the time, like again, if it's a maybe a, or like a maybe int whatever, then like fair enough, the tag is definitely important. But if I just have a maybe int, right, I don't need the tag, because then the maybe int would evaluate to an int or nothing, right, a just int or nothing. But like int or nothing is unambiguous. There's no morphism to nothing that overlaps with int. So then for those instances, right, like let's say I am accessing a list, right, or an array of ints, right, and then I want to have a get operation that takes an index and then returns the elements, right, and then for outer bounds it will return nothing. Like in that case, like I don't need to wrap it in just. Like if I want to get 5, I can just send 5 or nothing, right, and it's unambiguous. So with tag inference, for those cases where you can infer what the tag is, then it would allow it. So it's like an example I had somewhere here is this, right? So like let's say I have a maybe int, Okay, so it's a maybe of maybe int. Now nothing is ambiguous. Nothing is just nothing, right? So nothing would. So let me try to split this up. So let's say I have maybe. So for the maybe int, the first maybe is the outer one. Okay, actually no, I'll say outer and inner. Okay, so you have the outer maybe and then the inner maybe. The inner one is maybe int. The outer one is maybe int. Now for this example, nothing would be for the outer one, right? So the outer maybe would evaluate to nothing. For just nothing, the inner one would evaluate to nothing. So you have an outer nothing and an inner nothing. Okay, and then you have, but then for the int parameter, there's only one way that it can be int, right? So a maybe int is either a maybe int or nothing, and that inner maybe int is either an int or nothing, right? In that situation, there's only one int. Therefore, if I pass an int to this for this type, like 5, then it is unambiguously can be inferred as being a just 5, right? So here I have these 3 lists, and I know it's small, but I have these 3 things. Just 5 is equivalent to just 5, which is equivalent to 5 in this case, because it's unambiguous. And therefore these aren't errors, these are perfectly valid, and then nothing and just nothing are distinct. Which isn't that confusing, to be honest, because the tag of having the just in a maybe type is literally just for that edge case where I do have a maybe int, right, or like a maybe something. So like there's no need to have that for the general case, which is where I don't have a maybe nothing something, and like I have a very clear maybe concrete type or nothing, right? That isn't nothing. So like there's no need to do that. So then I kind of have that here, and like there's like you can view this as a proof, right? So like maybe int would expand to just int or nothing, right? And then if we expand this, like expand these parentheses, we get just int or just nothing or nothing, right? And then from here we can see, okay, well, where is just actually needed, right? So nothing and just nothing, those both take the same type. So nothing and nothing is a type. Just nothing is a tag, right? So there we need some kind of distinction between a just nothing and a nothing. That's fine. But for int, there's no other int in these other fields. So just int can be collapsed to just be int. So then we get simplified it to just maybe int is int or just nothing or nothing. And that's effectively how that works. Or in yeah, or with syntax that's a bit nicer for me personally to read, is that. But same idea. A maybe of integer is an integer or some none or none, right? Integer only shows up once in that entire thing, so it's unambiguous. So that's the first thing. I was also thinking just like generally about like how if you have a type A, right? So a type variable A. From now on, if I say A, B, C, whatever, I mean like a type variable. If I have an A or a unit type, then that's an A unit type. But if I have A or void, right, where void is the empty set, it is the type that has no morphisms going to or from it. Well, yeah, to or from it actually. Void is like it's essentially inaccessible. If I have an A or void, because void is inaccessible, the type that I've created is effectively just A, because there are only morphisms to A, which I can access, but there are no morphisms to void. So void is basically just a dead field. It's not only is it inaccessible, even if I give it a tag, it would still be like just completely pointless to even try to access. I don't even know if void has like the identity, void to void. I guess it could in theory, but I don't know if that's even like can I pass void to a void constructor? I don't know, maybe not, because again like it's the empty set. So maybe maybe it doesn't even have the identity. I don't know how that works with the category theory, but if we have void as a type in the language, then adding void to a sum type would basically just be a null operation. It'd be a no-op, right? Similar to how adding 0 to 1, right? 1 plus 0 is 1. Nothing changes. Likewise, adding void to A So by adding, I mean making a sum type, adding to the list of like options, a or void would just be a. So that's the first thing. And then for product types, if I have a and void, right? So an a and void, then that would make the whole type inaccessible. A and void equals void, essentially, because if I have a product type, right, that means that each field now has to be accessible. With a sum type, no, it's like this or this, right? So if I don't, so I can ignore the other ones if I don't want them. For an and, for a product type, I can't ignore the other ones. So if void is inaccessible, it's not constructible, then my entire type becomes inconstructible, and therefore I cannot have and therefore the entire type becomes inconstructible, i.e. it becomes void. And for units as well. But anyway, I mean, so that's analogous to saying that 1 times 0 equals 0. Okay? And then multiplying by 1, though, I don't think that works here. Like, if I say a and a unit type, I mean, yeah, I mean, like, also, like, for unit type, you could say that a and unit type, so the product type of a and a unit is just a, because unit is like it doesn't really do anything. Unit is always the same, right? It's always unit. So having a and unit is kind of pointless. You might as well just treat it as an a. But I haven't really thought about this, so that too deeply. I don't think that matters so much. But anyway, just another thought there. Then the other thought was with tags in general. So for tags in general, right? Usually, what is a tag? So I give the simple example. This is Rust notation, but imagine whatever language, C++, C, whatever. If I have a language where I can overload functions, and I know that you can't in Rust anyway, so that's whatever. If I have a language where you can't overload functions, then I can't have, that can overload functions, then this case here is ambiguous. Because I have a function called load data, and one takes a string file path, and one takes a string network address, right? And that's it. They're both of type string to data. And in a language that ignores function argument names or function parameter names, then this cannot be resolved, because it doesn't know if it's a file path or if it's a network address. I could fix this by creating a new type called file path and network address, right? And like having those be strict. So if I pass a file, so like a file path is not coercible to a network address, and then that would work. But like that's essentially what having tags is, right? It's creating a new type with this information encoded. So instead, what I can have is a language that just adds the name, right, the field name to the type. So this is no longer a string to data. This is a file path string to data, and this one is a network address to data. And now it's no longer ambiguous. What's weird though, in languages that do have field names, usually the way that you tag a field name, or specify a field name, and the way that you specify an enum or ADT tag, right, a sum type tag, is different. Like in Rust, it looks like having like file path, and then like in parentheses the type string, right? Whereas in a product type, it's just file path colon the type string, which I find weird. So I want to find a way to kind of unify that. So that was the other thing. And then another thing, which I believe is the last thing, was how I go on this notation. So like so far, I've been using the bar to mean a sum type or, and the ampersand to mean a product type and. But the reason I did this was because I didn't want to confuse people by overloading plus and, the plus symbol and the asterisk time symbol, because that's already used for numbers, right? Like 1 plus 1 equals 2, If I were to overload that so that int plus int equaled, a sum type of int or int, that would be a bit confusing. But then I realized, you know what? I don't care. Like it's like the language is building on category theory, so those who use the language should be familiar or made familiar with category theory. And like it's not like it's that confusing anyway. Like it's if anything, it's more confusing to try to make different operators for them. Because like plus is analogous. Like plus, like adding types is somewhat analogous to adding numbers, and multiplying numbers is somewhat analogous to multiplying types. Which is to do with like the whole reason it's called product. Like there is a reason it's called a product and a sum type, because it's to do with the cardinality, but also the kind of semi ring behavior of how adding 0 to a number, right, 1 plus 0 equals 1, is analogous to adding void to any type. So like, I mean, here I use unit, but like 5 plus 0 is also 5, right? Int plus void is, or int or void is int, right? So int plus void is int. Same for multiplication, 1 plus 0 equals 0, right? Likewise, as I said before, if I have any type times void, it becomes void. So int times void is void, units times void is void, right? That also works. And then if I have plus and times, it means that I can add other operators, right? Other operators, without having to worry about inventing even more symbols. Because like I have ampersand and the bar, right? But what about like exponentiation of types, right? Like if I want to have a like a maybe squared int to be short for maybe int, like I can't do that without then reusing the power of operator, unless I only use that operator for types, and then for like for numbers I have to use like a function. But like that's just, again, like it's confusing. Instead I can just double up and say, yeah, 2 squared is 4, is 2 times 2. Likewise, maybe squared is maybe times maybe, or maybe like a product type of maybe maybe. So I get maybe of maybe, sorry, maybe and maybe of int. So it's a maybe int. Or like it's a maybe int and a maybe int. Hold on, does that make sense? Why would maybe squared of something be maybe of int? Of something. Yeah. No, yeah. So like maybe squared of int would be maybe int. Okay? But maybe int squared, so maybe of int then as a whole squared, would be a maybe int and a maybe int. Right? So like int squared would be an int and an int product type. But if I have maybe squared int, then it's just of that. Right? And it's interesting because I can apply this to anything, right? I mean, like a maybe int is just like a type definition that takes another type, kind of like a function. So a function could also have this, right? I could have sine squared just work in the language naturally, without it being like a special rule. Like that's just how the operators work. In the same way that I can exponentiate numbers, I can also exponentiate types, because like they're both values. So sine squared x would be sine of x, which is literally what sine squared is. Sine squared of x is not the same as sine of x squared, I think. Sine of x squared is sine of x times sine of x. Whereas sine squared of x... Wait, is that even right? Let me just confirm that. Sine squared x. If it's not, then I have a problem. Okay, kind of ignored my symbol for some reason. I hate how Google just like ignores some symbols. It's actually kind of confusing. Oh, okay, hold on. No, sine squared of x is actually equal to sine of x squared. Okay, that is quite problematic. In that case, I guess maybe of int would not be sine maybe squared. It would be a maybe int and a maybe int. Which, like, I mean, like, it makes sense anyway, because like maybe squared would give you maybe a and maybe a, and then if you apply that to like a value, then a is becomes that, right? Okay, I think that might come up later in the book anyway that I'm reading, so I'll look into that as well. But okay. But that's just one operator. The other operators are minus and divide, right? So like if I can do a plus b, so like an int plus string is a sum type, then I should be able to subtract that, right? To do the inverse operation. So I should be able to take an int or string, subtract int from it, to just get the string, right? As a type. Likewise, if I have a times b, so a product type of a and b, and I divide it by a, then that should result in just b. So if I have an int and a string in one type, dividing by int should remove int from it and just give me the string type. So that works. Yeah, but exponentiation I need to look more into, because it can't be an exception, it needs to be consistent. Like typically exponentiation means this, like x squared would be x times x, right? So by this logic, a maybe squared would be maybe times maybe, or a product type of maybe and maybe, which is a product type, which is not the same as nesting. Nesting is different, so I need to look into that. And there's one more thing, which was a bit kind of interesting. So negative numbers, right? What is a negative number? What is a negative type? Because if I can have int minus string, or like whatever, or like int and string, like int times string divided by int, right? Or int plus string minus string. What does it mean to have a negative number? And this took me down this kind of thought rabbit hole, where negative 10 is not really a number as much as it is a function. It is a function of x minus 10. Because if I apply negative 10 to a number like 5, I get negative 5. But the issue is, negative 5 then is, also a function. So then what is 5? It's not applying negative 10 to the value of 5. It's applying negative 10. Sorry, it's composing the functions negative 10 and positive 5. So minus 10 and plus 5. So 5 is also a function. But what is it a function of? Well, if we assume that the starting point of numbers, right, the number, let's say, is 0. What is 1? Maybe you've seen this before if you've ever studied proof. 1 is the successor of 0, right? So if we have a function called successor, succ, suck, right, and we apply it to 0, or call it on 0, then we get, well, the successor of 0, which we can define with a symbol of 1. So 1 is equivalent to the successor of 0, right? We're just giving a symbol or a label to that function, successor of 0. So then 2, which also has a symbol, is given to the successor of 0, or the successor of 1, right? Because the successor of 1 is equivalent to the successor of 0, which we call 2. So we've given another label to it. Because again, like, keep in mind, 1 and 2 are not like related to 0 in any way, like symbolically. Like, they are very arbitrary symbols. The names 1, 2, like in English, like those are things we have made up to give labels to these things that we call numbers. Really, we could think of them as just being functions. So again, successor of 0 is a value, right? But the successor function is not a value. It is a function. So 2, the function of 2, would be the composition of the successor with the successor, right? It is the successor of the successor of 0. Well, no. It is the successor of the successor. That's the function. Jesus Christ. Point is, there it is, right? So then what is negative? Negative 1 would be the predecessor of 0. But the predecessor is just defined as the inverse of the successor, such that if I have the successor of the predecessor, then I get the identity. So there are 3 functions here. The successor, the inverse, which is the predecessor, and the identity function, right? So the identity of 0 is 0, the identity of 5 is 5, whatever. But the successor of the predecessor is the identity, such that if I have the successor of the predecessor of 0, I get 0 back. right? Which is an interesting way to think about numbers. So really, the only like number that really exists is 0. Like that is the unit, right? Like the unit is in zeros. 1, 2, 3, 4, 5, whatever. It's just defining the successors of zeros and the predecessors of zeros. And then you also have like multiplication. So multiplication would be, I mean, it's defined as like, oh, like it's abstracting, right? Addition. So if I have 3 times 2, it's 3 plus 3, right? So like it's just kind of like making it more compact, but and likewise division would be the inverse of that. But yeah, it's interesting. So it means that for a negative type is just the inverse of a positive type, where a type in itself is a function on the unit type. So the unit type would probably be the empty set, right? Void is the empty set. And then if I had void plus int, then I'm adding it, and then that becomes int, right? Void plus int is int, because then it creates a sum type where I either have void or I have int. But void itself has no morphisms to or from it, so it's just int. Yeah. And if I add int to int, and then tag them, then I have twice as many possible values, right? Because they're tagged. If they're not tagged, then it's a problem. But because then they just kind of merge into one type int. So like, now does that mean that void has a successor function? Not necessarily. But I mean, like, the successor of void, defined how we did it here, would be void or something, right? And then the predecessor of void would be whatever takes it away. So if I have a void or int, then if I subtract int, I get void. So like there is like some duality there, right? Like one is analogous to the other. But point in case, I want to have the language built up in this way, such that that it will make sense to add types in the same way it makes sense to add integers, right? But yeah, I do need to think more about then, like, what is an integer, right? Like even when we see numbers, right? Like when I see a negative number, if I say that the altitude of something is negative 20 meters, right? That probably means below sea level. So it's sea level minus 20 meters, right? A negative number is always going to be relative to something. In the same way that a positive number is relative to something, right? A positive number, if I say the altitude of Mount Everest is, I don't know, 200 kilometers, what I really mean is it's sea level plus 200 kilometers. Or someone's age, right? If I am 10 years old, I am 10, well, I am the birth age, right? The birth counter, which is 0, plus 10 years. So like from the moment of my birth plus 10 years. That's what I mean when I say I'm 10 years old. Now, is there a negative age? No, because you can't go before that time. But no, like I could say, I don't know, negative, you know, when I was negative 50 years old or whatever, which would imply 50 years before I was born. Very weird, you know, we don't say that in natural language, but like that's what that would intuitively mean if you had to give it a meaning. So yeah, like they're functions in that way, which is interesting. They're functions applied to some kind of starting point. So the question is then, what is the starting point? Is the starting point a value? Is 0 a value? Or is 0 a function? You know, when I say 5 plus 0 equals 5, you know, 0, I guess, is just the identity function then. Right? Because then if I compose those functions, I have 5, so plus 5 composed with the identity function 0, which equals 5, or plus 5. It's kind of interesting. Yeah, yeah, yeah. And what else was there? Yeah, but anyway, I mean, this was today, so like I'm still kind of thinking about this. A question I still have is like, what like, I know that types overlap with sets, right? Like the set of, I don't know, the set of positive integers less than 10 would be 1, 2, 3, 4, 5, 6, 7, 8, 9, right? And like that forms a set of possible values. So a set is really a sum type then, right? Like a set gives you the possible states, 2, 1, 2, 3, or 4, or 5, or 6, or 7, or 8, or 9. So the set of like 1 to 3, 1, 2, like 1, 2, and 3 is 1 or 2 or 3. So then a product type is a tuple, right? It is the set of, I don't know, like if I have a product type of 1 and 2, and like that's the only possible state, then my set is just the tuple 1 and 2. But then like how's that look in the language, you know? Like when I add sets together to get unionization or whatever, you know, the union of those two sets. And then like how do I get tuples from that? Or product types, you know? So I'm still thinking about that. And like whether or not I want to kind of expose that kind of interface. Like have like a set facing interface. Because like how do I disambiguate 1 plus 2, as in the numbers 1 plus 2 equals 3, or adding the sets of 1 and 2, right? Like there needs to be some kind of thing about that. Because like 3 is not the set of 1 or 2, you know, or 1 and 2, it's not. 3 is just the function. Like this here is function composition. This here is the union of two sets. But then like is a set also a function that is, you know, being added to the empty set? I don't know. I don't know. Like one way that you could think of addition is that 0 is the empty set, and then the successor of the empty set is the set of empty sets. Yeah. And then the numbers that we take from that is just the cardinality of the set, right? So the cardinality is the number of elements in the set. So if I have a set of empty sets, then the number of members is 1, right? Well, actually not even though, because like then 2 would be the successor of the successor, which is the set of empty sets. And that's 2. Yeah, so actually no, it's not cardinality, because then what is the set of the empty set and the empty set? Is that possible? I don't know. Or the set of the empty set of the empty set of the empty set of the empty set, you know, and like subtraction is like what? Removing a layer of like nesting? I don't know. But then like if 0 is the empty set, then but then like that's the empty set, you know, like what is then the set of int, you know, or like a set containing the set of integers, like how does that work then? I don't know. It's something to look more into, but like as I look into this, because like I can make a programming language that is atomic in terms of like bits, you know, like the binary representation of a computer. I can do that quite easily, you know, like your atoms are your bits, and then just define a system. Well, I say just, that's where it gets difficult, but define a system where you can abstract over it. But to do that, like to be truly atomic, I also need to have a unit of abstraction, right? An atomic unit of abstraction. How do I do that? So then like you have to look at like the root of everything, right? What is 0? What is addition? You know, what is 5? Is 0 the root? You know, the unit's value is that, like, it's called units. Are units values the atoms of abstraction? I don't know. So that's what I need to research. So right now, I'll even talk to thingy here, Claude. Claude verified that what I was talking about is actually an existing thing. Integers as the Cayley regular representation of integer plus whatever. Also, keep in mind this only works on integers, right? Like this doesn't explain complex numbers. It doesn't explain decimal values. You know that they go less than 0. Sorry, that are between 0 and 1. Like what is 0.5? You know, and like yeah, maybe it's 1/2, but then like what is? I mean, what even is 1/2? You know, like 1/2 is multiplying by 0.5, but like what is division then? If not just the inverse of multiplication. I don't know. So that's like a whole other question, because we have numbers more than integers. Also, there was something else. Boolean algebra is also a semigroup, or a semi ring, sorry, for addition and multiplication. False plus false should give you false, because you get false or false. But true plus false should give you true. And true plus true equals true. But true times true is true, true times false is false. And false times false is false. But like, my point is, plus is or, and times becomes and, in Boolean algebra. So true and false being false is actually saying true times false, because false is the unit of multiplication, whereas true is a unit of addition. So if I add true to something, true is the unit of multiplication for Boolean algebra. So if I multiply anything by true, then it becomes... if I multiply anything by false... okay. Forget units. I'm thinking of like the dominance value, kind of. If I multiply anything by true, it becomes false. If I multiply anything by false, it becomes false. If I add true to anything, I get true. So false plus true is true. True plus true is true. If I have a plus true there somewhere, then it would evaluate to true. If I have times false, right? So again, or false. No, and false. Sorry. So if I have true times false is false. If I have false times false is false. Like whatever I have times false in, it's false. If I have true times true times true times true times true times true times false, it's false. In the same way that if I have 1 times 1 times 1 times 1 times 1 times 0, it's 0, right? So that's the sort of thing. And then like, do I have and or as operators, or do I just have plus? I don't know. Because like there are limited symbols. I can't remember what I was talking about. I think Boolean, right? Boolean. Question is, right, so like, yeah, anyway, so I think what I was saying was, you could have many different symbols to mean the same thing. So like, addition of Boolean values could work, like, you can use plus and times in the same way that you can use plus and times for numbers. Or for strings, you know, maybe adding, or well, I mean, strings are a list, right? Adding lists, you know? How that work? Like, adding the empty list, right? We're adding the list. Multiplying by, like, how do you go from a list to an empty list? Through, like, an operation. But, like, no, but, like, what do you multiply it by? If that even makes sense. Void? Like, add a void element so the whole list becomes invalid? I don't know. Or, like... I don't know. Let me ask. Would it be possible to use plus and times for many different types? Including numbers, booleans, and lists. Characters like chars are just mappings from like numbers to symbols. Like it's nothing special. Like you could add chars and like just have it be the same as you would be adding numbers. Right, so for numbers you add and multiply, right? For bool you have or and. For lists and arrays, there's concatenation and Cartesian product. I see. Right. So adding it 0, multiplying is 1. Oh, no. Sorry. The question isn't what do you multiply to get an empty list. The question is what do you multiply by to get the same list. So yeah, you add an empty list, that's obvious. For multiplying though, how's that work? Cartesian product. Oh, units. That's right. No, that makes sense. Because again, the product type of something and units is effectively just the something, because the unit doesn't add any information. Okay. Cartesian product of a list. Yeah, that makes sense. I mean, it's what Haskell does, doesn't it? But isn't it interesting that then we actually get concatenation for lists as well? You know? Like the age-old question of, do we have plus overloaded to add lists? It's now answered with a yes, because it makes sense. And sets of unions, timing, so multiplying is intersection. Or product. The intersection of two lists is only the values they have in common, right? Right? So like a set 1, 2, 3, 4, 5 and a set 2, 3, 4, their intersection is just 2, 3, 4. Or, well, bad example, but whatever. Yeah, the empty set. Boolean numbers will satisfy distributivity, exactly, and list concatenation, Cartesian product does too, up to isomorphism. Reordering pairs. So this isn't just notational cuteness, it's the same reason sometimes a product type is already called sum and product. 2 design decisions to nail down. What times means for list is ambiguous in practice. Most languages use list times n for repetition, not Cartesian product. Yeah, but that's times a number, that's different. If you overload times as a semi-ring product, pairs, that will surprise anyone coming from those languages. Yeah, I don't care. You need to pick one and be explicit. Bool isn't a ring, only a semi-ring. There's no minus, true. Yeah, like an inverse of true. Right? So like is or, right? It's like true or false is true. How do I get true or false and then like minus true? Like, can I do that? Like 1 plus 1 minus 1 is 1. So if I have true or false minus true, or 1 plus 0 minus 1 is 1. Sorry, 1 plus 0 minus 1 is 0. So true plus false minus true would need to equal false. How? Subtracting true makes it false. Subtracting false makes it also false, I think? No, so subtracting false wouldn't do anything, I think. Like, or false is a no-op, therefore the inverse of a no-op is also a no-op. But subtracting true would make it true. So the opposite would have to make it false. How'd you do that, right? Like, or... I don't know. You could define the inverse of or, right? So if we look at a truth table here, for or, right? So the inverse of this like if we have 1 plus 1 equals 2, then 2 minus 1 equals 1, right? So true or true is true, and therefore true inverse, let's say I or for inverse, true I or true is true as well, that's fine. True or false is true, but true I or false should also equal true. So again, false doesn't do anything. However, if I have false or true equals true, then true I or true should be false. So, and then false, false, false. So basically it'd be like this, but this one is false. So it'd be true, false, right? Like replace this symbol with our inverse or. So you get true inverse or false is true. False inverse, sorry, what? True inverse, no, sorry, it'd be here. No, so sorry, so it'd be false, true, false. True inverse or true should be false. But so TF is true, FT, well, like, what's FT then? Like, it makes it false, right? So I guess false. And then false, false, false. So yeah, so it'd be false, true, true, false. Does that exist? XOR? Is XOR just the inverse of OR? Is XOR the inverse of OR? I.e. the minus to plus? The minus to OR is plus? A semi-ring trait type class had int, bool, list, set, all implement. The same way Haskell's num overloads plus times across numeric types. The interesting design work isn't kind of over. I do the semi. Yeah. So let me look into the semi-ring. Also, what types do form a ring? Like what are the requirements for a semi-ring and a ring? Category theory, ring. The category whose objects are rings with identity and whose morphisms are ring homomorphisms that preserve the identity. Oh, okay. Right. Right. So it's a concrete category. Objects are sets, okay, with additional structure, addition and multiplication, and the morphisms are functions that preserve this structure. So is it only multiplication and addition? Oh, no, but this is as a concrete category, right? So there's a natural forgetful functor, ring to set, which sends each ring to its underlying set, thus forgetting the operations of addition and multiplication. So it takes a ring and makes it a set. Okay, I guess. Properties. Initial object, terminal object. The product of rings is the Cartesian product of underlying sets. Coproducts. Free products. Right. So yeah, this is really interesting. Isomorphisms are bijective. Monomorphisms are injective. Oh, I didn't know monomorphisms existed. I was like, yeah, regular is another term I've heard of, but I don't really understand it. Right. It's the plus for different, better behaved structure. Bool or and is an idempotent semi-ring. Sorry, so what's a semi-ring? A generalization of rings, dropping the requirement that each element must have an additive inverse. Right. So rings require that they must have an additive inverse. Do they also require a multiplicative inverse? Multiplicative, I don't know, inverse. Yeah, Boolean algebra is the smallest semi-ring. Logical disjunction is addition, so or, and it doesn't mention multiplication. A semi-ring is a set R equipped with two binary operators plus and times, called addition and multiplication. Okay. So you have R and plus, which is a commutative monoid, and then R times, which is also a monoid. Is it not also commutative? Further, the following axioms tie to both operations. Through multiplication, any element is left and right annihilated by the additive entity. Right. Oh, okay, wait, hold on. So the additive entity is what annihilates it. Okay. And then multiplication distributes, yeah. Damn. So, in that case, again, addition, for addition, the additive entity, i.e. the thing that does nothing, is false, right? If I say true and like whatever, and then say or false, the or false doesn't do anything. Therefore, false is the annihilator. But left and right, by the way. So it's the left and right annihilator for multiplication, or and, right? And that's true. If I have false and anything, it's false. If I have anything and false, then it's also false. So that works completely fine. But that's a semi-group. Or semi-ring. So then what is... So if that's a semi-ring, and I look at rings, Where's the ring definition? Wait, this is different. Okay. So a ring is a set R with two operations, addition and multiplication. Okay. So an R is an abelian group under addition. Okay. So plus is associative. A plus B equals B plus A for all A, B, and R. So plus is commutative. And these are axioms, right? Yeah. Abelian. There's an element 0 in R, such that A plus 0 is A. That's the additive identity. And then for each A in R, there exists negative A, such that A plus negative A equals 0. So that's the additive inverse. Right? Also, R is a monoid under multiplication. Okay. So it's associative, and there's an element 1, such that A times 1 equals A. Okay. And multiplication is distributive. So A times B plus C. Okay. That's it. So the only difference between that and a semi-ring is that a semi-ring lacks the minus, right? Okay, and also a generalization of bounded distributive lattices. Man, should I study maths? But like, I feel like if I took a maths degree, I'd have to pay attention to so many things I don't care about. The smallest semi-ring that is not a ring is a two-element Boolean algebra. For instance, with logical disjunction, as a motivating example that is neither a ring nor a lattice is a set of natural numbers, including 0. Neither a ring. I mean, I don't know what a lattice is. Semi-rings are abundant because a suitable multiplication operation arises as the function composition of endomorphisms. Sure, bro, sure. Some authors define semi-rings without the requirement for there to be a 0 or 1. A group and a semi-group. Yeah, so what's a group and a semi-group? A group is a set with an operation that combines any two elements of the set to produce a third element within the same set. So 1 plus 2 equals 3. Just an operation. Hold on. Have a look at that. Semi-group. I don't know. Because I've seen a group in Haskell and I've seen semi-group in Haskell, I think. Oh, no. The group is a set. What's a ring? Just an algebraic structure that consists of two operations. Okay, hold on. I mean, this said semi-ring, right? Idempotent semi-ring, idempotent communicative monoids can't have inverses at all. There's no x with a or x equals false, unless a is already false. So OR has no subtraction, not even XOR. It's structurally excluded. Why don't they just add it? Or I guess it's just like it just doesn't exist, therefore it doesn't form one, right? Bool XOR AND is a genuinely different algebra. XOR is commutative, false is identity, and every element has its own inverse. It's its own inverse. This makes Bool XOR a full ring. What? XOR and AND is a full ring? In fact, a field, GF2. What the hell's going on? So if you want Bool to support minus, you get it by choosing XOR as plus, not by pairing minus with OR. But sorry, you said it's its own inverse. So in that case, plus and minus are actually equivalent. Anyway, that's crazy. Does that even work? Ah, that's weird. What forms a ring is an abelian group. So t plus 0. So integers, rationals, reals, complex numbers, z over nz. Oh, mod. Bool under XOR AND. Polynomials over any ring. Matrices that are n times n, so square matrices. Functions t to r with pointwise ops for any ring R. Not rings. Semirings only, no minus. So not natural numbers, because there are no negatives. Bool under or and, list string under concatenation. You can't unappend something. True. And set. Right, so like, all the things that we usually do in programming, we want semirings. Right? Like, we want booleans, we want lists, and we want sets. Those will be semirings. For true, we have two traits, semiring and ring, which extends semiring. And you implement semiring for plus, right, and 0. Okay. So does Haskell have semiring? Haskell semiring. It does. So if anyone asks me, why I'm not a big fan of Rust, this is why, bro. It doesn't even try to do the cool thing, you know? Like, as far as I'm concerned, it borrows or steals or takes some ideas from Haskell and applies it to its language to make it, like, I don't know, a more expressive, not even expressive, a more, I don't know, like an easier to use C++, besides for the bar checking side of things. Like more easy, like easy for the compiler to verify, more verifiable. But apart from that, it doesn't do like the interesting things. Like you can't compare Haskell to Rust because like it just isn't even the same ballpark. And even Haskell itself, like it's cool, but it has limitations, you know, that I guess Liquid Haskell might even address. But I mean limitations where like they weren't even sought to be solved in the first place. Like, as far as I'm aware, Haskell was made as a research language for lazy evaluation. All this other stuff is kind of just, like, additional, I guess, that they wanted to try out. But, like, a functor in Haskell is not, it isn't a true functor in the same way it is in category theory. I wonder why that is, but, you know, I barely understand what a functor is anyway, so I'll have to come back to that. So, semiring A, where the class of semirings, yeah. Okay. So they should. So by the way, when it says should satisfy the following laws, I believe that these are not enforced because they low key can't be. Like the compiler has no way to enforce these laws, which is one thing. Of course you could make like tests, but these are on the same page, right? Yeah. So 0 plus x equals x, x plus 0 equals x plus y plus z equals x plus y plus z, x plus y equals y plus x, 1 times x equals x times 1 equals x. So for bool, the additive monoid is bool or false, and the multiplicative monoid is bool and true, right? Which is interesting. So can I create two different instances? And is there a general operator? Is it called plus and times actually? So if I go to the Haskell playground, and I want to import data.semiring, okay, and let me print true plus false. Should be true. Cannot find module data.semiring. It says Haskell 98. So I don't know why it wouldn't be included. Haskell import semiring. Yeah, I mean it's the things. Holy Haskimony. What does that mean? Is that the name of the the thing? Wait, what? I don't know. 2 monoids is 1. In Holy Haskimony. What does that mean? Is that a quote? I'm very intrigued by this. Matrimony. I see. Yeah, two monoids is 1 is a good way to define it, right? Because you have the additive monoid and the multiplicative monoid, and that forms a semiring. Why can I import it? GHC, I don't know, 14 then? Like, is it not? Core, ASM, nope. That's weird. Let me find a different one. That's a blog. Import data.semigroup. Unless you can't import it, but surely you can. It works here. Print true plus false. Yeah. Okay. Haskell import. You import and then the symbols. Okay. Yeah, but no, but it should import everything now. Yeah, qualified and unqualified names. A bit confused by that. But okay, so the minimal complete definition, plus, times, 0, 1, and from natural. What does this mean? 0, 1, or from natural. Is that what that means? Here's annihilation. So you got plus, A to A to A, 0, which is A, times, and 1 are from natural. So here's some instances. It's weird. What are these? Infix shorthand for plus. So plus takes a semiring A to A to A to A. Is it though? Because like if I go Haskell playground, what? I can't do like I can't print true plus true or true plus false. Yeah. No instance of num-bool, right? So like what's going on here? Is this even Haskell? It says package, right? Hold on. But Haskell has semirings, no? Or is this not built into Haskell? Maybe not. Semi-groups. Okay, so Haskell has semi-groups. This one's built in, right? Yeah, it says base 4.22. So this is included. Type A is a semigroup if it provides an associative function, like this. Is that it? That can't be it, right? That's it. Okay, fine. And it combines them into one. So I assume that I can do true and false. There's no semigroup bool, so I can check what it exists for, right? What's S times? Repeated n times. Okay. So there's byte array, void, all, any, event. Non-empty. First, last. Okay. So is it like 1 plus 2? No? It's ambiguous. Okay. But I can do like foo and bar, right? I wonder what that is. Are there any languages where like they built in support this? Hold on. Are there any languages that have built-in support for this? Like, I'm aware of a data.semiring package for Haskell, but it's not part of the prelude, I think. Or even just like the way that things are built up in general. Pure script. I just acted in lean. Okay. I really need to check out lean or an Agda and IJS. Because like those are the languages that like are most related to what I want to do. Is pure scripts built in? Okay, so if I go into pure script, play around. By the way, I've checked out pure script before, but I kind of ignored it as like a, well, just like Haskell basically, but for functional programming. I thought about using it though, once upon a time, but I just didn't find it that appealing, like with this, like I really don't like this syntax. That's my main issue. But okay, so let me import prelude. Let me remove all this code. This is JavaScript output, by the way. Can I use PureScript to just show, like to just print? Unknown value print, right. How do I use this without? There's fold. Can I just render hello? Say no, right? Text. H1. That works. What's the error here? Doesn't tell me. Can I use H1 directly? No. Cannot match type record with function inline. What? Okay. I guess. Effect unit is interesting. So small on my recording. It's crazy. Yeah, sorry. It's way too big. So let's say I render this plus world. Does that work? Right. So no typecast instance was found for a semi-ring string. Why not? Is there a plus plus? Nope. Is there this? Okay. So this seems to be a semi-group for strings. Can I textify this? Can I show? Okay. True or false, is that a thing? No. True or false? Yes, okay. So can I do plus? No semi-ring for Boolean. What's the point then? It literally is a Boolean. Okay, that's just weird. Boolean via a wrapper. Why doesn't it just have it by default? Okay. Let me try lean. Or lean versus active, first of all. Leans improves just for general purpose type programming. Agda is a research platform for programming type theory. Right. Also, it's type theory. It's not even like category theory. Which language would be best to try these out in? I've looked at pure script just now, but the lack of the lack of default support for Boolean and string semi-rings put me off. It's weird that no language supports this by default. Right, let's check out just 2 here. What is this, bro? This hurts my eyes. Main IO. Puster learn hello edges world. Okay, it looks very Haskell-y. Right off the bat. Which I didn't expect. I mean, I don't know what I expected it to look like, but I guess not Haskell. Is int bool to type. Okay, we have named parameters, it seems. Which is good. True, false. Int or string is int. Int or string is int. What? Let me actually read this. I'll go to start to find out what first class types mean. In practice is the free. Okay, so it does first class types. Okay. You can write functions to calculate types. Oh, I see. Yeah, I didn't read it. Int or string literally returns true. If it's true, it's an int. If it's false, it's a string. Show reverse. If it is an int, it asks for an int. If it's not an int, it asks for false. Sorry, it asks for a string. Jesus, my head. So if it is a show, otherwise reverse. Okay. Contrived as this may seem. Maybe a list. They reverse the cons and type operators, so it's kind of funny. Is there a playground for this? Need to install it. Comments use 3 bars. Okay. I don't like underlying. I don't understand why that's a thing. Module main IO. Put Sterling. I guess it's for like keywords and stuff. Hello and welcome to iJust 2. Functions are implemented as by patch and matching. Additional natural numbers can be defined as follows, again taken from the same library. Why is a natural number Z or S nat? What's Z? Integer? Oh, 0. Okay, natural number is 0, sorry, that's just really not obvious, is it? 0 or successor. Can you use 0 as a symbol? So nat to nat to nat. Yeah, so if it's Z plus Y, it's Y. Okay, that's cool actually. I'm guessing I can do the same in Haskell, right? Data vector nat to type to type. So nil is a vector of type vector Z, A. That's natural number 0. Type is of A, and it's nil. So vector of type 0 is nil, okay. And there's a cons operator which takes the type Oh no, it takes the instance. That's right. An instance of a, but nil isn't a function. So how does it return an a? What's a here? Just the type. I don't get that. Okay, I think I should look at this sometime and give it like a proper like read, because that might be the closest to what I'm actually trying to do right now. Is there not an agreement in maths for what multiplication on the list is? Concatenation is the multiplication. Yeah, okay. I thought it would be. To be fair. What even is the difference between, the addition and multiplication for a semi-ring? Because for a semi-ring, it removes the... Like a ring here, right? Okay, so multiplication must be distributive in respect to addition. Doesn't say anything about the destruction. Let's look for semi-ring. So for semi-ring, there's plus and times, and what connects them, is that for multiplication, the additive identity will destroy it. So the first thing you need to find is the addition, right? So for like concatenation, multiplying by an empty list would have to destroy it. So if I multiply 5 by the empty list, I get the empty list. Now for Cartesian product, that makes sense, right? Like the unit would be 1, so the 1 would be unit. I mean the list of unit, because then like if I have 5 and 3, right, and I multiply it by the list of units, then 5 times units. Sorry, then I get the tuples of 5 in unit and 3 in unit. But anything and units is just the thing, because the unit is doesn't add any information. For 0, so the empty list, when I do the Cartesian products of that, there's nothing to multiply by, therefore I get an empty list. So so global's wrong. So it is times to concatenate two lists, which is weird, right? Also, it's not really concatenation, is it? Like, am I thinking of sets, maybe? For a list, if I have 1, 2, and then 3, I would expect to get, like, if I multiply them, I would expect to get the Cartesian product, which is the tuples 1, 3, and 2, 3, not concatenation. Concatenation, I guess, could be plus, maybe. The semi-ring structure you're thinking of shows one level up on the sets of lists. I mean, sure, but like that's just sets in general, right? A buried list is only a monoid, not a semi-ring. There's no canonical plus for a single list. I mean, it's not kind of arbitrary if it's times or not. Oh, because okay, hold on. What distinguishes addition from multiplication? Right, distributivity. But that's if you have plus and times. So that doesn't work for this case. Okay, plus is always required to be commutative, times isn't. Multiplication can be non-commutative. Right, so here, because what? Concatenation is not commutative? List concatenation isn't commutative, yeah. They're different. So it would be defined as multiplication. In a ring, plus must have inverses, and times does not need to have 1. Okay, so division isn't actually required, which is interesting. For or and, they're symmetric. False and x equals false, yeah, annihilation. True or x equals true is not a requirement. So if or was times, then plus would be and? Yeah. So if plus is and, then the annihilator is false, right? So the annihilator would become... No, sorry. The zero operator, whatever. So if plus is and, then false must be the annihilator for or, times, but that is not the case. Okay. So for true... Okay. Okay. Interesting. So sets form a semi-ring, right? Which is why it might work for types. The trivial semi-ring. 0 equals 1. What? Okay. So semi-ring, a ring adds the requirement that plus must have an inverse minus, such that a plus negative a equals 0. So why aren't sets rings? Why don't sets form a ring? Can't subtraction be removing an element from a set? Indepitant. The union of A and A is A. What does that mean? Idempotent. Idempotent. Where does that even come from? Something you can do multiple times, but it only changes the system on the first try. Okay. So like false and true is... Sorry, true... False or true is true, After that, you just get true, 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 true again. Like repeating it doesn't change anything. Whereas with addition, it does change. Also, like, is that a requirement? Idempotent commutative monoids can't have inverses at all except for the identity. Proof: if X were A's inverse, A join X equals empty set. It's a semi-ring. Needs to satisfy A and B disjoint A, which only holds when A is a subset of B. So it's not a group inverse, but it is a real operation. Interesting. When I multiply int and bool, I'm technically multiplying a set, because I get the Cartesian product of int and bool, or the set of int and a set of bool, which is int cross bool. So should I... okay. Swap this for symmetric difference. So symmetric difference works as a semigroup, or a ring even, sorry, the power set ring. Wow. Do the bool and set semi-rings with XOR and symmetric difference. Symmetric difference is like everything but the middle, right? Yeah. Like, it's literally just XOR. In fact, when I was learning about this, I remember going crazy trying to link this to Boolean algebra. I was like, dude, I swear symmetric difference is just XOR. And it is. It is XOR, effectively. But it's XOR and right? Because XOR gives you the outside, and gives you just the inside. Likewise, the inside. Likewise, some symmetric difference is this. An intersection is just the inside. I mean, it's Boolean, isn't it? I mean, Boolean is like are Booleans and sets not literally analogous? Just that Boolean algebra acts on like the set of two possible values, true or false. So that makes sense. So if I have the intersection of true and false, it's false. But the intersection of false and false is also false. I don't know. Okay. They're the same ring. Holy moly. Sorry, I didn't say that. Have use in programming. What if they replaced the standard bool and set? That doesn't make sense, does it? Because like you can do XOR anyway, but what would or look like? And types are semi-ring, right? Yes, but of real load-bearing uses. Binary addition. A hardware half adder is literally A XOR B. Carry A and B. Error correction, cryptography, what? Set reconciling, diffing. Really? Short circuit evaluation. A XOR B. Yeah, you don't know from the first element or even the second element. They need to match. It's just interesting because like here both can mean plus, right? Because it's a semi-ring, both can mean plus. They just have different operations. It's kind of weird. I can have a boolean. Okay, I can have a boolean type. And use plus for both XOR and OR, and both would be valid depending on whether you want a full ring or semi-ring. Yeah. Bool needs 2 semi-ring instances rather than 1 canonical plus. So what should true plus false mean? The inverse are true plus true or XOR. That's true actually, yeah. Plus some was a compile error unless an instance is explicitly chosen. That's a bit confusing though, isn't it? Default plus to or times to and. A new type for XOR. That makes sense, yeah. Connected to I can't speak. Connected to type. Interesting. Very interesting. Okay. Yeah, because like, what is a type again? A type is like a collection of morphisms almost. So, and also like possible states. But like a type is a set of possible states with morphisms. So bool, while being true or false, it also comes with the morphisms or an and, right? Or plus and times. So I can have a different type, which again is true or false, but has different morphisms. Question is then, are they coercible? I guess they should be, right? It's fairly powerful. Here's an idea. Two different Boolean types. The semi-ring bool and the ring bool. I didn't get how I'd call these, but rig bool or semi-ring. The semi-ring has plus equals, has the monoids. What's the notation for this even? The notation for this. Bool under or and. Plus is or, and times is and. The ring, the complete ring, has plus XOR and times is and. And even for sets, which is weird, like even types, right? And then even types need this distinction. The semi-ring type has plus as union and times as intersection. Is that even true? Intersection? Because we're thinking of product types. Yeah, I don't know. Sets also need this distinction. Yeah, it's just a bit confusing, isn't it? Because for sets, plus is effectively, yeah, I mean it's union, and times is Cartesian product, not intersection. Or plus is union and times is intersection, right? So the empty set for intersection would be destructive, it's just empty set. Yeah. For both semi-rings, times can be Cartesian products, or but it can also be intersection. right? I guess one is like changing the type though to tuples. What about sets? Can't times be either Cartesian products or intersection? Semifields don't have a multiplicative inverse. Or a field, sorry. No. So a semifield is a semi-ring when it has a multiplicative inverse. They pair different plus. So intersection pairs with union. Cartesian product pairs with disjoint union. Oh, what? Right, sorry, no, yeah, because disjoint union, I believe, keeps duplicates? Am I right? Cardinality. Right. What's a disjoint union? Yeah. And tags them. Okay. And even for types. Wait, no, I'm wrong. A true set has plus as union and times as intersection. Types, however, have plus as disjoint union and times as Cartesian product. Disjoint is where the tags come in. So having optional tagging creates a set. And then it's no longer then that's no longer a Cartesian product, is it? Unless, yeah, union and Cartesian products as a pairing technically satisfies distributivity too, but nobody uses it. The universal set is the identity of intersection. No, not intersection. What union? So they must be disjoint. So yeah, so it is a semiring. However, plus as normal union and times as Cartesian product is also a valid semiring. And it's low-key what I want with the tag inference model. Well, no, not tag inference. That's different. I just want int or int to be int, you know. By cardinality. A and B is an element of A Cartesian product B and C. If and only if. So what that means? A is an element of A and B is an element of B or B is an element of C. Okay. The empty set is still the plotted entity, so A Cartesian product that equals that, yeah. Is cleaner than disjoint X since ordinary union needs no explicit tagging. The pair's position, first, second, or disambiguates which side an element came from. For products, yeah. Yeah, because like for products, disjoint union requires tags. But only on... Does it need tags for even product types? No? Yeah, maybe. I mean, first and second already disambiguate it, but that's if you want order. So like think of first and second more as like implicitly added tags. Word breaks for your purpose. Cardinality stops being a homomorphism the moment the operands overlap. Int plus int needs 2 times int inhabitants. Why? Because you can have this with optional tagging and it will still work. How would they be separate named instances? I don't get how I could have them as separate named instances though, since I want my type system to use this for its sets of possible values, states. I'm thinking that it therefore makes sense to go for this one, since it's more flexible and leaves tagging as optional. And it makes sense to use this one for my type system, since it's more flexible than enforcing disjoint unions, since tagging is optional. Int equals int, but left int or write int does not equal int. Correctness of exhaustive checking and pattern matching, which depends on the type checker actually knowing how many distinct states exist. Leave tag optional is best to put our flag hardest. Tagging isn't an extra feature built on disjoint union, it's a reason that is avoids a collapse. Making optional isn't by flexibility, it buys the type system that's correct only when operand types happen not to overlap. But does that not mean that even... But what if I want a or int such that if a equals int, the type collapses to just int? Well, then it has to be a or int, but... TypeScript is both? Or TypeScript just as one? TypeScript enum. What? Okay, fine. TypeScript some type. Okay, whatever. So the AND is for intersection. The intersection between two types would be with AND. It's weird actually, yeah. So there's plus and times, but they can overlap with different definitions, and there's no way to disambiguate them. Like to disambiguate them. You either have one definition, or if you have both, you need some kind of way to distinguish them, like through namespacing or something. But like that kind of defeats the whole purpose of operators, right? Mm. But a plus int wouldn't compile anyway. Like we need different names for these types depending on what operations they do, right? But things like a set has all these operations. Like a set will have, or like an easy example, a boolean will have XOR and an OR. All, all, all you're selecting is which one is for plus and which one is for times. Otherwise, all the functions still exist, right? So, why have... Yeah, so like, it means that plus and times are just kind of arbitrary? Yeah, I don't know. So it seems like plus and times are chosen rather arbitrarily. Which poses issues. It means that reusing them for types and booleans and whatnot means I'm making fairly arbitrary choices. What is true plus true? It could be true if plus is OR, and it could be false if plus is XOR. Both form valid semirings. So both are possible. And that's only considering semirings. Some combinations also form complete rings, like XOR and. Again, how do I disambiguate, right? Wait, so how do mathematicians go about disambiguating what plus and times mean for different categories? Structures are named tuples, not properties of a bare set. A mathematician never says, does Bool have a plus? They say, consider the structure bool or and false true. Or consider bool, XOR, and false true. The set is just the carrier. Plus and times are a part of what's being specified, not inferred from the set. This is why bool can be two different semirings with no conflict. There are two different structures that happen to share a carrier set. And you disambiguate by naming which structure you mean every time explicitly. Yeah, so like if I had two different names, right? For bool, like OR bool and XOR bool, right? Then although the structure is the same, the morphisms are not. Very weird. Very weird. I mean, the morphisms are the same though. Like OR and AND are the morphisms. It's just the semigroup is different that I define to have plus and times. So like I can choose one, but then for someone to choose another one, like how do they do that? And like as a programmer, you don't want to have to like keep track of these either, you know? Like, if I see the same operator used between two booleans, I'm gonna assume it's just one thing, and like sometimes it's OR and sometimes it's XOR depending on like the type, because like I can't tell what the type is based on the identifier, right? Category theory disambiguates plus and times structurally via universal properties. Oh, does it? A coproduct plus isn't some operation that feels additive. Is defined as whatever object A plus B is, equipped with injections. Any pair of maps out of A and B factors uniquely through A plus B. That universal property applied in the category set forces the answer to be a disjoint union. Plain doesn't satisfy it. You can't recover which side the element came from. So the unique factorization part fails. Product times is the dual universal property, and in set that forces Cartesian product. Right, I think universal properties come up in this book later that I'm reading. Product times, yeah, and okay. So it's not that mathematicians chose disjoint union for plus and that by convention. The universal property is the definition, and disjoint union Cartesian product are the unique after isomorphism things satisfying it in set. Some same universal properties in poset as product and coproduct. The category theory answer is one that actually satisfies the open question, some type. Does the category theory approach work for booleans? For instance. Does it even work for integers? Or are they like two different things, you know? Or and, cleanly. Don't look at bool as an object in set. Treat bool as a category, yeah. Product equals meat. Coproduct. False bottom is a coproduct identity. Join A and B, A or B. Wait, so it's called join and meet? Weird names, to be honest. This is a real instance of the general pattern from heap 4. Same universal properties, different category. But not XOR. And integers. Apparently what solves this ambiguity is the universal property. is universal properties, but I'm yet to understand them, so I'll pick this back up once I've covered them. But what they do say is that for sets, is that for the category, set plus is disjoint union and times is Cartesian product. And that Bool, and that the category Bool is has plus as and, no, or, and times as and. Right, so Bool, hold on, instructive. Yeah, or an and. There's a caveat. You should carry into true universal properties for you given the category. They don't set up which category to use. Universal properties settle this versus this for you given the category. It's true. Like, this is set, right? Integers aren't a product of some object the way bool or and, where meet join. Instead, integers and natural numbers are characterized by an initiality, being a unique up to isomorphism object with a universal property in two stages. N an F algebra is any object X with a map 1 plus X to X. A choice of 0 element plus a successor function. Okay, that's what I was going on before, right? For integers, it's the natural numbers keep completion, or equivalently the initial ring. Formally, the set of integers is universal among rings for any ring R. There's a unique ring homomorphism that the set of integers to R, sending 1 to R as 1 and generating everything else via plus. This pins on plus and times and 0, 1 simultaneously as one package. Which of these two mechanisms does type structure come from? Wow. This is deep. By the way, why is inverse x to the power of -1? Like 2 squared, -2 is inverse, right? No, but yeah, so whatever. For a monoidal group under an operation written multiplicatively, x to the power of n is defined as x composed with itself n times. Oh. Just change his answer. That's weird. In group theory, x to the power of n means apply x's operation n times. Yeah. No. So x to the power of a composed or times x to the power of b equals x to the power of a plus b. For that to hold at a equals 1, b equals negative 1 equals 0, the identity. Yeah, that makes sense. So why is it that in high school maths, sine to the power squared of x is sine x squared and not sine of x? And why is then sine to the power of negative 1 x not the inverse and not 1 over sine of x? Sine negative 1 is cosine. Arc sine. This one's a genuine inconsistency, not due principle. Worth naming is different from anything before it. There are two different monoids in play for a function, values under multiplication and a composition. No, sorry, values under multiplication and functions under composition. Right. Sine squared x uses the first convention, historically just a compact way to write sine x squared without extra parentheses. I mean, just put it after the x, because trig functions get squared constantly. Why did they just put it after the parentheses? That's really weird. Sine negative 1x and switches to the second convention. Okay, so like it is an actual inconsistency. So high school notation silently uses both monoid structures on the same symbol depending on the exponent sign. It's a wart. So in more careful text, use arc sine. Okay, so I'll note that too. Note that too. I should not support sine squared x being sine of x times sine of x. It's an annoying inconsistency in maths. All because someone thought sine squared of x would be less tedious than sine of x squared. Even though sine of x squared exists. Yeah. And it's why sine of negative 1 x means something completely different to sine of x to the power negative 1. Yeah, so if you want sine squared x, it will apply it. Do I also support the inverse function? Probably not, right? Like, how would that work? How would I automatically create the inverse of sine? It would need to like reverse the code somehow. But like how? I don't know. like times 2, to take the reverse of that, the compiler would need to know that the inverse of times is divide, and divide by 2, right? But like, how is it going to do that? Anyway, so I'm gonna leave it there for this recording. Did not mean to go this deep into this, but what I've learned is that I need to look more into universal properties, and that should make things a bit more clear, hopefully. And yeah, man. Woo. Woo-hoo-hoo. Okay. So I do want to try my best to have plus and times used for types as well as numbers, and for it to make sense, right? I don't want it to be arbitrary. I want to have that be the choice based on specific, like, unambiguous rules coming from, I guess, category theory. Yeah. Because, like, just, like, creating symbols for things, like, I'm not a fan of using different symbols for things that aren't even necessarily different. Or at least for things that have clear patterns that can be abstracted. Like, if plus and plus and plus here and plus here and plus here work all in the same way, because it's some unambiguous rule, I want to have those symbols. Especially because maths can make whatever symbols it wants to make, right? And like whatever different ways of writing, like the letters, like A, you know, with like different fonts and like different bold and whatever underlining. But I can't do that for... Sorry, why is this so... I can't do that for... Oh, no, for a programming language. I can't do that for a programming language, because I don't have all these symbols at my disposal, right? Like, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Not really 11, 12, 10, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. Like, roughly 27 symbols, not including parentheses, or braces and parentheses, and brackets. 27. And, like, most of those are already used for stuff, you know, like the quotation marks take 2, and those are used for strings and chars. Yeah, like comma and period. You could have those for something, I guess. Slash and question mark. Like, I want to use as few symbols as I can. If there are patterns, I want to take advantage of that. But it needs to be natural. It can't be arbitrary. So, we'll see. We'll see what I can learn from my next readings.